Today we're tackling three of the biggest, most mind-bending mysteries in all of physics, and how the Euclid Space Telescope can pave the way to solving them. We're talking dark matter, what is it actually made of? Gravity, did Einstein actually miss something? And dark energy, why is the universe expanding faster over time? We're digging into the details. I'm Ben, this is Physics or Bust. First up, dark matter. This is the invisible glue that holds galaxies together. Except we can't see it, touch it, or interact with it in any way except with gravity. Now we believe it's there because of rotational velocities in galaxies. According to Newton's laws and Einstein's relativity, the outer stars in a galaxy should end up rotating slower, just like the planets in the solar system. But they don't. They move too fast. Way too fast. Kind of like a roller coaster that somehow speeds up at the top of a vertical loop. The solution? There must be extra mass, creating extra gravity. 5 times more than all visible matter combined. So what is that mass? Here are the leading candidates. First we have WIMPs. No, we're not talking about me in elementary school. WIMP stands for Weakly Interacting Massive Particles. WIMPs are heavy particles that barely interact except through gravity and the weak nuclear force. If they exist, they could be 100 times heavier than a proton. Theory suggests that they were formed in the first fraction of a second after the Big Bang and froze out as the universe cooled. Scientists are looking for WIMPs using underground detectors like Lux Zeppelin, which is sitting under a mile of rock in South Dakota, but nothing yet. Second, we have axions. Axions are ultralight particles, maybe billions, even trillions of times lighter than an electron. Unlike WIMPs, they don't behave like normal matter. Instead, they're more likely to act like a field spread across the universe instead of individual particles. If axions exist, they could explain why the strong nuclear force doesn't violate certain quantum rules like charge parity symmetry. The ADMX experiment, Axiom Dark Matter Experiment, is literally using a large magnet to listen for axions to become photons in a resonant cavity. Third, we have primordial black holes, and this is the one that Euclid will give the best chance of either providing support or proving false. Instead of exotic particles, some theorists suggest that dark matter is actually just a collection of tiny black holes that formed right at the beginning of the universe. If these exist, Euclid could detect them via gravitational lensing, where the black holes bend light that's coming from behind them from more distant stars. The type of high-resolution detail that's needed in order to do this research is exactly what Euclid was designed to do. What do you think dark matter is? A ghostly particle? A quantum field? A bunch of rogue black holes? Let me know in the comments below. And if Euclid can spot weird gravitational distortions, we might just have an answer. Alright, here's a wild idea. What if dark matter isn't actually real? What if it's our understanding of gravity at cosmic scales that's wrong? Similar to how we have different rules that particles play by at the quantum level, maybe our understanding of gravity at the cosmic scale needs some different rules. Right now, our best theory for gravity is Einstein's general relativity. It works beautifully for black holes, planetary orbits, and even gravitational waves. But at galactic and cosmic scales, things just don't add up. Here are 3 major alternative gravity theories. First, we have MOND, which stands for Modified Newtonian Dynamics. MOND proposes that at extremely low accelerations, gravity behaves differently. It adds an extra boost to gravity in weak fields, which by design takes care of the rotational velocities at the edges of galaxies. The catch? MOND struggles with galaxy clusters, which show extra gravitational effects beyond what MOND would predict. The next theory we have is called emergent gravity. Proposed by physicist Eric Verlinde, this theory suggests that gravity isn't a force at all. Instead, space-time itself might be something like a hologram. And what we think of as dark matter is actually just the way that information is structured in the universe. This theory is extremely new and lacks observational evidence, but Euclid could help test the theory because of the detail and breadth of high resolution that Euclid's going to provide. Third, we have the theories that postulate extra dimensions. Some versions of string theory or brain theory, other brain, propose that our universe is a brain floating in higher dimensional space. If true, gravity could be leaking into another dimension, making it appear weaker at larger scales. It's possible Euclid could detect subtle disturbances in galaxy distributions that suggest extra-dimensional effects. Basically, if Euclid finds gravitational anomalies that don't match dark matter predictions, we could be looking at needing an entirely new theory of gravity. No pressure, right? Last but not least, dark energy, the mystery force accelerating the universe's expansion. We discovered the universe's accelerating expansion in 1998 by measuring Type Ia supernova. These stellar explosions serve as standard candles to measure cosmic distances. But instead of its rate of expansion decreasing due to the gravitational attraction of all the mass in the universe, its rate of expansion was actually increasing. So what was causing it? The first theory looks at the cosmological constant. Einstein's blunder might just be real after all. If true, dark energy is just a property of empty space, exerting a constant outward pressure. Information from Euclid mapping 1.5 billion galaxies will be utilized to see if dark energy behaves the same over time, since looking at objects that are farther away means looking at objects that are at an earlier time. Second, we have quintessence, or dynamic dark energy. Instead of a fixed value, dark energy could be a changing scalar field that evolves over cosmic time. If true, Euclid should see subtle variations in galaxy clustering in different time eras. So dark matter, new physics, cosmic craziness, Euclid might finally get us answers. But no matter how many answers we get, I believe that we'll end up with some bigger questions in the end. Let me know your thoughts in the comments below. If you enjoyed this video, I think you'd like this book. I have an affiliate link in the description below. I do get a small commission, but it doesn't cost you any extra. For more space and science news and updates, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.